In modular construction, BIM is much more than a digital drawing tool. It becomes the digital backbone of the entire project. Unlike conventional construction, where many problems can be solved later in the field, modular construction requires decisions to be made much earlier. Modules may be fabricated hundreds of miles away from the final project site, so there is very little room for field improvisation after production begins. This is why the building must first be assembled virtually. The BIM model allows the project team to coordinate the structure, building systems, openings, connections, and finishes before materials are ordered, cut, or installed. When BIM is used effectively, it supports clash detection, connection verification, assembly simulation, model-driven fabrication, and site installation planning. It connects design, factory production, and field assembly into one coordinated digital workflow. In this sense, BIM helps transform modular construction from a collection of separate building parts into a predictable, coordinated production system. BIM supports several critical functions in modular construction. First, BIM supports design for manufacture and assembly, or DFMA. The model helps divide the building into repeatable modules and assemblies. It can also include fabrication-level information such as framing members, rebar, lifting inserts, and connection details. This helps ensure that the design can actually be manufactured. Second, BIM enables automated clash detection. In modular construction, many MEP systems are installed inside the modules before they leave the factory. This means that pipes, ducts, conduits, and fire protection systems must align precisely at module-to-module connections, often called mate lines. BIM allows these conflicts to be found digitally before fabrication begins. Third, BIM supports 4D logistics planning. By linking the model to the schedule, the team can simulate crane locations, swing radii, staging areas, delivery sequences, and installation order. This is especially important on tight sites where just-in-time delivery is required. Finally, BIM can support digital twins and safety planning. With GPS, RFID, IoT sensors, or other tracking systems, project teams can monitor module location and delivery status. The model can also be used for safety reviews and virtual training so workers understand lifting, rigging, and connection procedures before they encounter them in the field. A successful BIM process does not happen automatically. It requires a clear BIM execution plan, often called a BEP. In modular construction, the BEP should be treated as a production control document, not just a modeling guideline. It defines who is responsible for the model, what software platforms will be used, how information will be exchanged, and what level of model detail is required at each project stage. One of the most important decisions in the BEP is the required level of development, or LOD. At LOD 300, the model may be sufficient for general design coordination. At LOD 350, the team begins to coordinate interfaces, mate lines, service penetrations, and connections between modules and site-built work. For modular production, however, the model often needs to reach LOD 400 before manufacturing begins. At this level, the model includes fabrication and assembly information such as framing details, connection locations, and installation requirements. The BEP should also require a Common Data Environment, or CDE. Since factory production and site work often happen at the same time, the team needs one reliable source of current information. Without a CDE, teams may work from outdated files, disconnected models, or conflicting revisions. A strong BEP helps prevent these problems by defining model naming rules, file exchange procedures, approval authority, revision control, and model use expectations from the beginning of the project. Even though BIM is powerful, it can fail when teams use it like ordinary design software rather than as a modular delivery tool. One common failure is siloed modeling and late manufacturer involvement. If the architect develops the model without input from the modular manufacturer, the design may ignore factory limitations, assembly line requirements, transportation constraints, or installation needs. To avoid this, the manufacturer should be involved early through design assist, design build, or integrated project delivery. Another major issue is inadequate tolerance management. Factory-built modules are produced with a high level of precision, but site-built foundations, podiums, or cores are usually less exact. If the model assumes everything will be perfect, modules may not fit when they arrive. Adjustable plates, slotted connections, laser scanning, and point cloud updates can help manage this risk. Software incompatibility is also a common problem. Architects, structural detailers, fabricators, and manufacturers may all use different software platforms. If the BEP does not define file formats and exchange procedures, important information can be lost during model transfer. Finally, teams must avoid over-modeling. More detail is not always better. Modeling every screw, nail, or minor finish element can slow down coordination and create unnecessary complexity. The best BIM model is not the most detailed model. It is the model that contains the right information for fabrication, tolerance control, MEP routing, and installation. The graphic, a residential project in Charlestown, Massachusetts, shows how BIM can support modular construction in a real project setting. The project included 125 apartment units made from 128 factory-built wood-framed modules placed on a site-built concrete podium. Many interior elements including drywall, cabinetry, tiled showers, lighting, and rough MEP systems were already installed before the modules arrived on site. Because of this, the project had very little tolerance for field error. BIM was essential for structural coordination. The project team used the model to trace load paths and confirm that structural posts in the wood-framed modules aligned with the load-bearing columns in the podium. This allowed the team to resolve structural conflicts before concrete was placed or modules were delivered. BIM also supported MEP coordination. Since each module contained its own plumbing, electrical, HVAC, and fire protection components, the team had to coordinate plug-and-play connections across all 128 modules. The model helped ensure that services aligned correctly with corridor systems and vertical chases. In addition, the team used BIM for erection sequencing. Module models were linked to the construction schedule so the team could study crane locations, swing radii, lifting requirements, and the order in which modules would be picked and placed. The key lesson from this case is clear. Early design freeze, a federated BIM model, and strong digital coordination can greatly reduce field conflicts and improve installation accuracy in modular construction.